All right. Three main topics we're going to talk about are shown here. The focus will be on systems. So far, all we talked about was signals. We started with learning different signals, different types. We classified them. And this lecture is going to be focused on systems. Different classifications of systems, and then we'll learn how to determine which group or subcategory they are allocated to. We'll learn about time invariant systems, system classifications, and a little bit about time domain analysis. Okay, so it's not difficult to determine if a system is time invariant or not. The way you do it is shifting your input signal and then check the output and see if it's shifted similarly or not. So if I shift or if I delay my input signal by 2 seconds, if the output is delayed by 2 seconds, then that's a time invariant system. So a system that doesn't change with time is called time invariant. Now, the way you can, or the method you can check this is by first delaying the input signal. Okay, so what you do is you first delay the input and then you find the output. Then, in the second step, you send the input to the system and then you delay the output and then you compare these two. So, literally what you do it's not recording. I don't know why it doesn't share the entire screen. Oh, I didn't select it. Cool. All right. So step one, that's your system. That's your input, xt. This can be your output, yt. Okay. So what you do is, for example, you delay this output, and then what you get is, call it y prime. Oh, let me choose another name for it. Yt minus t, for example. So you're delaying it by t minus t. Now, in second step, what you do is you first delay your input. So your output will be xt minus t. And then you send this into your system. And then you will get an output. And then you compare these two. If they are equal, then that's time invariant. Can you see the difference here? So it's just all about first delaying the output, and then in the second step delaying the input. We'll have a few samples, and that helps you understand this better. Now, it's the same for both continuous and discrete signal. So if you have n instead of t, if it's discrete, it's literally the same. So if you are delaying the sampling by 2 samples, your output should be delayed by 2 samples as well. Now, graphically, let's see if this is a time invariant signal or not. Now, your xt, the blue chart or graph, is your input. And that goes to your system, and it's equal to y, or your output x is x equal to t minus 3. So that's what your system does. So whatever you send to the system, it will be delayed by 3 seconds. Now, let's check. Let's delay the input and then see if the output follows the same pattern or not. Now, at the bottom, we are delaying the input by how much time? 2.5, yes, because we used to be between 0 and 1. Now we are delaying it by 2.5. We are sitting at 2.5 and 3.5. And then our output is shown as that, which is delayed by now delayed by you're saying 3 seconds? No, we are comparing the original output with the new input. Sorry? Nah. Okay, so I'm going to repeat it. I have an input, which is shown here, and that's my output, right? If my input is delayed by 2.5 seconds compared to the original input, how much the output is delayed compared to the original output? 2.5. Just compare the bottom one with the top one. So at the bottom, we delayed the input, and then the output compared to the original output is delayed by 2.5. So it's following the same pattern. Is it clear? No? Okay. So what I said was delay your input, see if your output follows the same. Okay? Now, forget about the yellow bit. That's your input, right? And that's your output. Now, to check, delay the input and see if the output follows the same. Now, how can we delay the input? By pushing it to the right. So I've delayed the input by 2.5 because I used to be here. Now I'm here, right? Then how did the output change compared to the original output? 2.5, yep. Because I used to be sitting at 3, now I'm at 5.5. Raising hand, who didn't get this? Cool. So that's literally what you need to do. So that was the graphical way of explaining it. The mathematical way is also as easy. Okay. That's literally what I drew here. So step 1, you send your input to the system, you get the output. Then you delay or shift by t, and then you have your yt minus t. Now this time, you start with shifting. You first shift and then send it to the system. So you're just changing the orders. And then if these two are equal, that's time invariant. It means that it doesn't change with time. If you shift the input, your output will be shifted as well. So the output is following the input. Now, why do you think it's important for a signal to be time invariant? Like your output to follow the input in terms of shifting. No,
how output follow the input.
No, just think about the practicality. What in?
The function the signal that goes into the function to not be disturbed or changed before.
No, not that.
Straight line.
Sorry?
That's a straight line.
What's a straight line?
It doesn't change the signal.
No, it will change. It's just shifted. So it can change like that. Now you shift your input. It still fluctuates, but it's delayed. Oh, by the way, you didn't send me your name. No. I heard something. Sorry? No. Okay, so let's look at a complex input, something like this. Okay? Now, assume that, forget about what you see up there. Assume that you're dealing with something like that at the bottom. Right? Now, if I consider this first bit, and then if I analyze it, and if I find the output to be like this, so I only take the first bit and spend time and money, develop some programs for it, so I can predict the output. How does being time invariant help me to solve the rest of the signal?
We can make the output by changing and making any changes in input. For example, the second part between 1 and 2, it's a shifting signal of XT with a scaling.
Exactly.
Time invariant.
Exactly.
We can
exactly
extract the behavior of output.
Exactly. So if we know the answer to the first rectangle, and if I can prove that my signal, my system is time invariant, it means that if I choose this second rectangle, because it's just the shifted version of the first one, right? It's just shifted by 1 second to the right, multiplied by 2, right? So I should expect the outlet to be shifted by 1 second and then multiplied by 2. Now, let's consider the third one. So this one. This one's the original signal is, or the one highlighted in red, is shifted by 2 seconds, right? And then multiplied by half. Now, I'm quite sure if I send that to the system, my output, which is up there, will be shifted by 2. So it will be something like that. the answer will start from 2 because I'm shifting it by 2, and then it will be half. So if that's my 3 and if that's my 4, I'm going to be sitting somewhere here. That's the answer, the output of that signal. Now let's see what happens to the, let me draw the second one as well. So this one is shifted by 1 second and then multiplied by 2. So it will start from this point and ends here, right? And it's multiplied by 2, so my max will be somewhere around here. So that's the, no. I should start from 2. So 2 will be my max, right? It goes up and then goes here. And then the last one, which is, I don't know, go with pink. So let's check this one. So that's this signal, but it's shifted by 3 seconds and then multiplied by -1, right? So if I shift the original output by 3 seconds, I'm going to sit at 3 to 4, and then to 5. And then I'm going to be multiplied by -1. So it will be like that. So all I did was finding the answer to the first rectangle, and then I could predict. That's why it's important to know if it's a system is time invariant or not, because instead of solving or writing a program or solving your problem for the whole input signal, you just solve it for 1 bit, and then you predict the output based on that. Raising hand, who didn't get this? Cool. All right. That's literally what I just explained. All right, so that was the important part. Now, it can be more complex, like what you see. So my input is that red line. It's not a simple step, let's say, signal. It's something like that red graph you see up there. Now, what we can do is, by a, I would say, accurate approximation, divide it into smaller rectangles and then follow the same process I just explained. So we divide it into, I don't know, 10, 20 smaller square, find the answer for one of them. So that's what we have up here. It's the first element. And then I send that element only to the system, and then I find the answer. So that's the answer. That's the output, what you see here. For the rest, I'm just delaying and then changing the amplitude. For example, for the green one, it's been shifted to the right or delayed by epsilon second. That's why the output is also shifted to the right. Look at the green line on the right. It's shifted by epsilon. And then its amplitude changed. By how much? So if I want to find the red line, the green line on the right, I should multiply the black line by a number, right? No, epsilon is how much it's shifted to the right.
What is the amplitude of green? It's a degree of amplitude.
That's my question. How can I find the green, hey, the green line? So I know if I shift it by epsilon,
This time invariant, if you shift it, it should give you the amplitude, right?
no, it shouldn't, because look at here. If I go back, so see, they have different amplitude. The red, the pink, the blue one. It's because the input has a different amplitude. Now my question is, I already know here that 2 and 1 is given to me. I know.
We can reverse it if you have the amplitude of output.
No, we need to find the amplitude of output. So see,
If we don't have amplitude of input,
we can find the amplitude of output. That's my question. How? Sorry? No. Sorry? No. Sorry? Exactly. No, that's correct. That's correct. So you need to find the ratio. What you do is, if I what I'll do is, if I call this A and that B, if I know the ratio of B over A, if I multiply my output by the same ratio, it gives me the output. Okay? For example, looking at this, I divide it into, I would say, 3 parts. And then I would say that's 1/3 higher than the original one. So just find the ratio, and then you can find the output. Now, this is an estimation. It's not supposed to be very accurate, because from the beginning, we are making approximations. We are not exactly sending the green line, the red line into the system. We are making rectangles that represents that red line. So that's the application. So it's not like it's not an unuseful classification. It's quite applicable, these time invariant signals. Now, memoryless. Another classification. If your output depends on the present or past, that's one way of checking it. The other way is to check if your output depends on the future value. So there are 2 methods to check this, and then I'll explain both. Now, memoryless output depends only on the present value of the input signal. Now, if you can find a value related to the past or the future, then you cannot say that's memoryless. Don't worry about these examples. We have better examples, and we will talk about them. Now, let's look at these. These are more tangible, I would say. So let's look at the first one. Yt is equal to 5xt minus 2 plus 2. So this one says it's a system with memory. Can someone explain why? So what was the definition? The definition was if your output or if your system depends only on the present. Now, looking at the first one, can someone propose a method to prove that this system has memory? Sorry? Nah, that's too complex. There's a simple. Sorry? Yeah. What happens at T0? You're getting very close. So the beginning, the first 50% was correct. Putting a value instead of t, that's the beginning. Now, let's consider that 0 you mentioned. What happens if I put t equal to 0? You're also getting close, but not what I'm after. Now, let me explain it. Let me explain it this way. Okay, I decide at this very moment we are sitting at t equal to 0. Okay? Let's say this moment is t equal to 0. I'm putting t equal to 0 in that equation. What happens? Sorry? Everything will be 0. Do you agree?
It depends on X, the type of causality. If it is causal signal.
No. We are talking about systems now. So it has nothing to do with the signals. So causal, non-causal, that was for previous lectures. This is a new lecture for systems. Now, okay, let me see. If I put t equal to 0, your friend says everything will be 0. Now, if I put t equal to 0, my y at this moment, y at time equal to 0, will be equal to 5x minus 2 plus 2. So what does t minus 2 mean? Time minus 2. Remember I told you we don't have negative time. Negative time, minus 2 seconds doesn't have a meaning. So what's the meaning of t equal to minus 2? It means the past from this moment. So if I say that's my t equal to 0, 2 seconds before that moment is my minus 2, right? It's in the past. Now, if you say in 2 seconds from now, it means in the future, 2 seconds in the future. That's t equal to positive 2. Now, what this tells me is that my y, or output at this moment, depends on my input at minus 2 in the past. So whatever x was 2 seconds ago, I need to know to find y now. So it has memory. It remembers past. All right? So the easiest way to do this is by just putting numbers inside. Change t to see if we can find one number that proves it has memory. It's as simple as that. Raising hand, who didn't get this? Okay. So I'll explain it again. let's start with the very first basics. Xt. Okay, that's the signal. And t represents the independent variable. It means that t changes, and then I will have a value based on that. For example, if I say that's my xt, that's the signal, right? And that's t, that's x. It means that when t changes, I have a value, right? That's the definition of input signal. Now, what I'm saying is that I'm sending this input signal into a system, and what this system does is multiplying 5 by my signal, delaying it by 2 seconds, and then adding 2 to it. So that's what it gives me at the output. That's what the signal, the system does, sorry. And that represents my y. So I say, okay, I call my output y, but it's nothing but my input being multiplied by 5, delayed by 2, plus 2. Okay? So that's what the system does. Now, this means that I can find the value of output at any time. If I change t, my input xt changes. So if xt changes, xt minus 2 changes, and then my y changes. So your output changes. Clear so far? Now, what I'm saying is that I'm going to say that's where we are. T equal to 0. That's where we were 2 seconds ago, minus 2. And then in 2 seconds, we will be here on time axis. It hasn't come, it's in future. So this means that if I put t equal to minus 2, it should give me an output. If I put t equal to 0, it should give me an output. And the same, if I put t equal to 2, it should give me an output. Because it doesn't matter what you send to the system, all it does is multiply it by 5, delay it by 2, and then add 2 to it, and give you the answer. Now, I want to see if this system has memory or not. And then the only way to prove it is that it remembers what has happened in the past or future. What will happen in the future, either of these. So what I'll do is, I'll assume that I'm sitting here. I'll check the system to see if it can remember any input from past. Now, if I put t equal to 0 here, it should give me y at 0, right? Because that's the output at 0. Now, y at point 0 will be equal to 5x 0 minus 2 plus 2. Or that's x minus 2. So what this tells me is that if I want to know what the system gives me now, I should go back 2 seconds, find x, find the input, because that's what the equation tells me. I should go back 2 seconds, find the input, or x, which on this graph maybe is here, minus 2. That's xt. That's x minus 2. And then multiply it by 5, and then add 2 to it. Yes?
What is confusing me is in relation to advancing or delaying signals.
Yes.
I don't know, maybe it has become different in this topic. But if we are shifting to the right, the origin from 0.
Okay.
If we are shifting to the right, that's negative. If we are shifting to the left, that's positive. So that's what is.
Why are you saying it's negative if you shift? The sign will be negative. It's because you're delaying it. So let me tell you that way. So, and I'm going to repeat this. We are talking about systems now. Okay, so what we talked about before in previous lectures about a signal being causal, non-causal, shifting a signal left or not, that was for the signal. Okay, we are only focusing on the system now. So if I say, okay, a signal can be memoryless, a system can be memoryless, and these two are not the same necessarily, okay? So you may be asked to find if a signal is memoryless or if a system is memoryless. So make sure you know the difference. Don't confuse this. Now, back to your question. That's what you're saying. If I have this, it means that my signal is shifted. So whatever I have, this one, if t is here, it will be like that. It will be shifted to the right. Okay? That's a signal by itself. That doesn't have anything to do with the system or the output. You know what I mean? So that's standalone by itself. It doesn't have a system. It doesn't have an output. So we are just delaying the input. All right. Any other questions? Okay, causal. Now you will see that it's, as I said, it's the total different definition with a signal being causal or not. Here, when we are saying a system is causal, it means that it only depends on past and present. So if you can find any future values in your system, then that's not causal. All right, can someone, I don't know, let me choose this one. Can someone tell me why this is not a causal system? Again, see here we have a shifted input signal, but we are talking about the system as general. Yeah, it has a shifted signal, so what? I mean, I can call. That's signal again. So forget about signal. So a causal signal. Let me go back. No, not necessarily. No. So you may have a non-causal signal input with a causal system. So it's not the same necessarily. Now, so I'll go back to the definition. It says it's causal if it only depends on past and present. So if I want to claim something is not causal, I need to prove that it depends on future. Or if I want to prove that it's causal, I need to prove that it only depends on present and past. All right? Now, I'll go back to, actually, I'll go forward to the next slide. This one is claimed to be non-causal. It means that I need to prove that it only depends on future. Because if I can find one sample or example that depends on present or the past, then it's causal. It's not causal. So can someone tell me how we can do this? Sorry? Okay, so exactly. So that can be an example. Yeah. So but it exactly. Yeah. So here, oh no, this is a causal, not about memory. So here, whatever time, and then again think about that time axis. Okay, what this tells me is that because my output is at time t, I assume that I'm sitting here. That's my present. Okay. So my yt is here, happens here. What this tells me is that if I put t, which is present, into that, my x will be t plus 2. So I need to find x here. Right? Now, no matter what your t is, your x will be taken from 2 seconds in future. Right? So put t equal to 1. Your x will be x3, taken at t equal to 3 seconds. So no matter what you put instead of t, your x will be taken in the future. That's why it's not causal. It doesn't depend on the present or the past. Okay, now someone tells me why this is causal. Yes? Yes. So whatever t you put, yeah, or, yeah, exactly. Or the easiest method is just put a number in there. Put t equal to 0, x will be minus 2. So it will be 2 seconds in the past. So you need just one example to prove that the system is causal. But to prove that it's non-causal, you need to discuss it, like the way I did. So you need just one example to prove what you have on the left. So that's what I do. Okay, that's my time axis. I would like to say this is my t equal to 2 seconds. Or let's say, just to make it clear, I'm going to call this second 0, the beginning. Now, my y at time 0 depends on x here, 2 seconds ago. So that's not causal. It depends on the past. What about the one below? Exactly. That only depends on the present because it's yt equal to 5xt. So if I put t equal to 0, my x will be 0. Put t equal to 1, y1, my x will be taken at the same time. So it only depends on the present. What if I want to get creative in the exam and then I say, okay, I'm going to say that's x minus 2, plus 2 minus xt minus 2. Now, is this causal or non-causal? Why not? Okay, what did you say? Because of the x plus 2. Yeah, that's correct. It's because of that x, that's xt plus 2. Okay, so, I don't need this bit. So I'm sitting here, t equal to 0, and I want to know the output at the same time, y equal to 0. Now, the first one is x here. So still, this is depending on the present. The second one depends on the future. I'm taking x here. and then that one, I'm taking an x here. So because of this one, I would say this is non-causal because I have one input from future. All right. Raising hand. Who didn't get this? Cool. So these are important. Time invariant and then the causal one. That one, so see, whatever we say about continuous signal is the same as discrete signal. Let me give you an example. Okay, now, if you remember last week, we said if we have, I don't know, discontinuous, and then if we take samples every 1 second, we will show this by right? I'm taking samples like that. Or the same, here will be so it should be symmetrical. Okay. Now, instead of saying assume that I'm sitting at time 0, you can say I'm sitting at sample 0 or sample 1, sample 2. The way you do it is, okay, if I have x, y, n is equal to xn plus 2, right? I'm saying that. Now, this is my sample 0. This is my sample 1, sample minus 1. The same for rest. So instead of time, I'm saying I'm sitting on the samples axis, and I'm going to call this sample 0. And my y at my sample 0 depends on, remember, that's my x. That's my input. I don't know the output. The output will be the advanced version of this. But that will be the signal type discussion. Now, my input, my output at sample 0 will be depending on x at sample 2. So, if I send this signal into a system, my output, that's my output, right? My output here, that's my sample 0, depends on this input, which is in the future. Right? That's what it tells me. It tells me y at sample 0 depends on, I can make it a proper system. So what this system does is multiply input by 5. So I put 5 here. So and then I can say add 5 to it, plus 5. Now, whatever goes into the system is multiplied by 5, then 5 is added to it. Now, I want to find the output at n equal to 0, this point. And it depends on a value in the future. So that's not causal. It's literally the same. All you do is you change the word time by sample. Vice versa, if this was n minus 2. So if I would say, okay, I have a system, whatever you send in is getting multiplied by 5, and then 5 is subtracted from it. And then let me go with another color, maybe green. Now, if I want to know the answer here, n equal to 0, my y0 will be 5x minus 2 plus 5. Now, the answer depends on this sample. That's in the past. All right, so whatever we have from this point onwards, it's not very important, okay? So either I'm going to skip some slides or I'm going to quickly go through them, meaning that either the content is too advanced, too complex, or is not useful for a general engineering perspective. Now, another classification is bounded input, bounded output. It means that if you send a limited input signal into your system, what comes out is also limited. So it's not like this is not bounded because it doesn't have any limit. It goes from minus infinity to infinity. And then if I send this into a system, the output may be similar. So if the system multiplies everything by 2, it will be like that. It doesn't have any limitation. Now, on the other hand, if I say, okay, I have this signal, 0 to 1, it's bounded. I'm sending it into a system. And then what comes out, it multiplies everything by 2. So all it does is this. But still, it's bound between two values. So that's bounded in, bounded out. Why is it important? The answer is on the right. Why don't we like, or let me tell it this way. Why do we like bounded output? Yeah, almost there.
Maybe because in the reality we don't have, don't know how to say it, but we don't have negative effects on
No.
maybe mathematically we can find negative numbers.
Okay.
But then we are gonna be subtracting.
No, that's not the answer. So let's look at this example. If we say, okay, my output, I can have a lot of inputs, right? Remember we talked about this in lecture 1. What were the inputs? No, simple inputs. So that's a system, that's a bridge we want to analyze. Wind, cars, number of people. So these are the inputs, right? Number of, I don't know, those cables, number of those columns. These are the inputs. Now, you are analyzing this bridge, and your output will be displacement. Would you like, yes?
You could have bounded outputs so that it's all like finite and you know it's more predictable.
Exactly. So you have control over bounded output. Because if your output passes a range, it results in failure. So, for example, assume that this bridge can tolerate the displacement of 10 centimeters. So if with all those inputs of wind, cars, people, the displacement goes over to 12, it fails. Or if it goes to 15, it fails. So what you prefer is having a bounded output, even if your input is not bounded. So that wind can be from 0 to 10 to 12 to whatever number it can have, but you want your design in a way that gives you the bounded output. Is there any way, can you think of any system or just make up a system that turns an unbounded input to a bounded output. Sorry? Sorry, I can't get it. No, not tunnels. No, I'm talking about something simple, a mathematical system. Okay, so just give me a system that if I send, remember I told you, for example, whatever this is, what this system does is multiply the input by 5, add 5 to it. So make up a system that turns something unbounded to something bounded, limited. Now, just give me something mathematical. Okay, if that's my xt, and if it's not bounded, it can go to infinity from both sides. So what I can think of, I can even give you a system that turns everything into 0 with no movement, for example, in that bridge. That, as simple as that. So what happens if xt goes to infinity? It goes to 0. Your output goes to 0. Yeah. Ah, you caught me. Wow, I hadn't thought about it. You're right. Yeah. Oh, yeah. That works. Yep. Problem solved. Or let's go smaller. I'll go with a very small value. Who said that? Send me your name. Okay? You saved me. All right. Cool. So then if you read these slides, you get confused. The explanations which you may forget in a few weeks. But if you think about what I said about that example of minimizing the output, then that probably sticks to your mind. Okay. All right. So again, not that important, but anyway, because it's given to me, I'm going to quickly go through it, but you will not get something like this in the exam. Those who passed engineering systems, Okay, so this should look familiar to you. It was the topic of lecture 4 and also your lab 1, modeling, draining or leaky tanks, buckets. So what we talked about in that unit was a very detailed mathematical method of developing a model or analyzing this tank. What's explained here will be more general. It's not going to be that detailed. Now, consider this tank. R represents flow rate. It can be volumetric, mass, flow rate, doesn't matter. R naught is your inlet, and then R1 is your outlet. H is shown as water level in the tank. Now, if I say I'm interested in knowing R1, so I would like R1, our outlet flow rate, to be my output. What can be the input? What are the input signals? R0, that's correct. H1. What else? There's one more. Sorry? No. Because we have summarized everything as R1. The valve itself affects the flow rate coming out. So if it's bigger, more water comes out, flow rate is high. What else? Is there any difference if I have a tank with this diameter or a tank with this diameter? Yes. So surface area of the tank is important, right? Now, if you compare it to engineering systems, what we had there was just numbers. We didn't talk, and I'll go again back to lecture 1, saying that the beauty of signals and system and why it's important for every engineering major is that you're not dealing with just one number. So see, your R is a function of T, right? So if we assume my R1 is this one, if I assume it as my output, and if I consider, I don't know, R0, for example, as my input, and if everything else, the tank, water level, its surface area, as my system, this changes with time, this changes with time, this changes with time. That's signals and systems, input, system, output. So when you hear signals and systems, you think it's electrical. It's not. Okay, it's a tool, it's a method you can apply to any engineering problem. An example is this. So let's see how we can apply signals and systems to solve this mechanical problem. Now, okay, now the changes in the level inside the tank depends on how much water you send in and how much comes out, right? So you can easily say proportionality. The difference between inlet and outlet defines the changes in my water level. So if the input is higher than the output, then the changes in water level is positive. Water level goes up, right? Or vice versa. If the output flow rate is higher than the input, dH over dt, which shows the rate of changes in water level, becomes negative. It means that water level goes down, right? That makes sense. So that equation is nothing but a simple analysis of what happens inside that tank. Now, why can I write the first equation as the second one? So everything's similar, but I'm saying that I'm replacing dH by dR1. Those who passed engineering systems. Bernoulli's equation.
Flow rate and level.
There's an equation called Bernoulli's equation. So search for it. I'm not going to go into details, but literally what it says is that the velocity here at the outlet is related to square root of 2gh. 2 times gravity or gravitational acceleration times water level. So water level is directly related to velocity at the outlet. And then volumetric flow rate is equal to velocity times surface area. That's valves. surface area. Remember, we are talking about here. Don't worry if you find this confusing, okay? As I said, it's not the topic of this unit. So anyway, velocity is equal to square root of 2gh, and then R, which is the flow rate, volumetric flow rate, is equal to velocity times surface area. So if you have that's a pipeline. If you have water flowing in that pipeline, if you know the velocity, V, and then if you multiply it by the surface area of that pipeline, it gives you the volumetric flow rate. That's the most interesting topic to me. Fluid mechanics, heat transfer. I love these two. So I'm trying really hard to avoid going into details. Okay, but that's it. That's why you can, instead of, because remember this is proportionality. I can say, okay, h, velocity is related to h, and then flow rate is related to velocity. So flow rate is related to h, water level. So I can simply say, instead of writing h1, I say dr, or derivative of R1 with respect to t is proportional to R0 minus R1. And then to change the symbol from proportionality to equality, I put C there. So C depends on a lot of factors. It's a number I put there just to turn that proportionality into equality. And then I write that C as 1 over tau. And this equation turns into the final equation. So it was 4 simple steps. Looking at the problem, saying that, okay, water level changes based on the difference between input and output flow rates. That's the first equation. And then I say, okay, water level is proportional to output flow rate. So I replace H1 by R. And then I put a C value. Who knows how to find it? And then I say, okay, I would like to call my C equal to 1 over tau. And then that tau is called the constant of the system. It depends on your system. So your system dictates that number. So this equation applies to any tank with any input and output flow rate, with any valve size, with any surface area. Because they all follow this. What changes is? Sorry? No, these are all the same. So between a tank this big, and this big, with different flow rates, the only thing that changes is that tau, or that C. Okay? If you can find C, it's the same for all those tanks. Now, this number, or this constant, it applies to any, let's say, engineering. Let me see if there is an example. Yep, there's an example of electrical circuits. You are looking at the final equation. Voltage, current, input, output with that C. C is your system constant. The solution itself, okay, I'll quickly review it, just because you may need it, but don't worry about this specific, as I said, problem or example. I'm just reviewing it for your information, you may get to similar differential equation, and you need to solve it. Now, 5 bonus marks if someone tells me how to solve this. So I'm going to give you 1 minute. Think about it. My aim is to find R1. Differential equations are math 1, I guess. You should know, you had engineering systems last semester. And I repeated this like hundreds of times. R1. You're getting close. Very close. No, you're getting far. Well, let me make it simpler for you. I'll solve the simple version. dy over dt plus y is equal to 1. No. It's simpler than that. That shows you need to review math if you don't know how to solve the differential equation. Okay. So unfortunately, you lost 5 bonus marks. All right. Don't worry. There are more chances. Okay. So what I'll do is, from math, I know, and it's already 1.5 hours, so I'll try to be quick, wrap up the lecture in 10 minutes, and then we'll go to a break, come back for the tutorial. What's the answer? Sorry? Natural log. Or log. L and U. Or, remember, differentiation is the opposite of integral. So, d over dt, L and U, the answer is? Sorry? U prime over U. Yeah, they're the opposite. So, if differentiation of L and U is U prime over U, integration of U prime over U will be L and U. So what I'll do is, I send Y to the other side, 1 minus 1. And then I replace right? I bring dt up, 1 minus y down. Now, let's build that u prime over u. So if u is 1 minus y, what's u prime? Minus dy. That's correct. Because 1, the integration of 1 is, the differentiation of 1 is 0 minus dy. Now, compare this u prime over u with this. Do I have u prime over u up there? Why do you say we do have it? So if I want to have u prime over u, I need to have minus dy over 1 minus y. But I have only dy up there. I don't have minus dy. No. I cannot multiply. Now sorry.
Minus from this side and minus what right there and minus.
Now you just need to add it to one side. So what I'll do is I'll put -1 here, right? Because these two cancel each other. One goes in the numerator, the other one in the denominator. And then what I'll do, I'll take the integral. I only need one of those minus signs, right? I'll take the one in the denominator out. It will be -1/1 integration of, or -1, minus dy over 1 minus y equal to dt. I chose the worst color, green. And then that's my u prime over u, right? What will be the answer? Exactly. Equal to, the right-hand side is t plus c. Thank you. T plus c. But I don't have y. I have ln 1 minus y equal to t plus c. Exactly. So again, math. Let me open. So I got to this point, minus ln 1 minus y equal to t plus c. Thank you. Now from math, we know if ln, I'm going to call it something y. If ln y is equal to t, y will be e to the power of t. So I'll do the same. Or I can take the negative sign to the other side, saying that ln 1 minus y is equal to minus t plus c. That's fine. It doesn't change anything because c is a constant. It results in the same answer at the end if you put values inside. So don't change. And then now I say 1 minus y is equal to e to the power of minus t plus c using this. Right? And then my y will be equal to 1 minus e to the power of minus t plus c. Okay, again, if you couldn't remember any of these, please review math. These are all your math units. All right, we have 2 minutes. Don't worry about the rest. You don't need them. Cool. Oh, by the way, this section here, there are, I don't know how many slides, 10, 20 slides. It's reviewing math. So if you couldn't remember what I just said, just quickly go through these slides at the end of this lecture. That reviews the whole linear differential systems and how to solve them. Okay? So if you don't have access to your textbooks or references for math units, just at least go through these slides. Let's have a break for 5 minutes. We'll start the tutorials.